That's how we're going to find the total impedance. We've got Z1 times Z2 over Z1 plus Z2. So where do I go from there with that complex arithmetic in rectangular form? Expand on economy more. Yeah, so 120 times J. 2 to 10 plus 12. What do I then need to do? Someone else. Common by the complex conjugate. Multiply what by that? Top and bottom. So we've got to do this. Brackets 22 plus 5J, 22 plus 5J. Effectively, if you do it to the top and bottom, you're effectively multiplying it by 1. Yep. But we know what that does. What does doing that on the bottom do? Cancel the you say, Carl, what you say? Something? Who said something? Cancel out the jump. Yep. What is it always the bottom line equal to? Can you remember? So underneath, from doing several of those, we know it ends up at 22 squared plus 5 squared. Yeah, because if you square a negative number, you'll end up with a positive one, won't you? Yeah. Top line becomes minus what? Yep. You looked at my answer sheet. Well, my final answer is wrong, is it? Have I? 250. Yeah, I can see that now, yeah. Just shows how easy it is to accidentally put an extra naught on something. Right. Jake's going to start teaching you now. So that combines overall to. What happens with this plus 250J squared? It comes J squared is minus 1. So it ends up as a minus 250. You've got to take 250 off that. 2390 minus 500J on the top, all over 500J. 2 squared plus 5. 509. I didn't care. I didn't do it. That don't sound enough to me. Hang on, let's just check this. Multiplying this out. 120 times 22, is that 2640? Yep. 120 times plus 5, 600 plus 600J. 120 plus 5, 600, isn't it? Yeah. So just to sum that question up for the video, we've got a capacitive parts of the circuit there, 2 in series, 12 minus 5J, and that's in parallel with a resistor, so we've effectively got that circuit. This is one of the formulas for calculating parallel impedance. Yeah, no I haven't. Wish I had. Okay. I'm showing off how bad my skills are. So that's calculating the combination of those two impedances together. So then we went on and used that formula with complex arithmetic to come up with a total impedance in rectangular form of that. And we just learned you need to be careful putting that in, because if you miss that negative sign out, it changes the sign of all these angles. That's that converted to polar. So we've got a negative angle impedance, which we would expect from a circuit with just a capacitor in it. If we had just an inductor, we'd get a positive angle. If we got both, we could get either, and more about that in science. Okay? Then we used Ohm's law with that correct version of the impedance in polar form. V of a Z, find the current in amps, and notice that when we do that, it changed the sign of that angle to a positive one. The current with a negative angle impedance, you get a positive angle current, and vice versa. Okay. What we're just going to do now is have a look at a mechanical example. Coplanar forces. Determine the magnitude and direction of the resultant of the 3 coplanar forces given below when they act at a point. So what we've got is this point in the middle here. We've got 3 forces pulling on that. 10 newtons in that direction, 8 newtons in that direction, 15 newtons in that direction. What is the resultant force of that? Its magnitude and direction. They are vectors, yeah? So that's like 3 currents being added together, or 3 voltages being added together in electrical. It's just that the units are newtons, they're forces instead of amps or volts and so on. So all we've got to do is add 3 polar complex numbers together. We've got to add 10 newtons, angle 45 degrees. We've got to add 8 newtons, angle 120 degrees. We've got to add 15 newtons, angle 210 degrees. Notice we've got no negative magnitude this time. So we're not going to come up against any kind of calculator errors. What are we going to do? The easiest way to add all them 3 together. Sorry? Change them to rectangular. Yeah. And then we can just add up the real parts, add up the imaginary parts, convert back.